Thank you for joining us today for our webinar, Permanganate and Polymer Feed Systems to Optimize Your Plant with UGSI Solutions, Gary Schaefer. I'm Ashley Swingle and will be the moderator for today. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with your question and contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. At this time, I would like to take the opportunity to introduce our speaker, Mr. Gary Schaefer. Gary has a civil engineering degree from Lafayette College in Easton, Pennsylvania. He has worked for over 45 years in the disinfection and chemical feed business with Wallace & Tiernan, US Filter, Siemens, and UGSI Solutions, holding management positions in engineering, marketing, sales, and international product management. He is an AWWA Life member and is currently a regional product manager with UGSI Solutions. I will go ahead and hand it over to Gary.
Okay, thank you, Ashley. I appreciate the introduction, and thank you, everybody. Appreciate your time today to listen to me talk about permanganate and polymer activation systems. I'm with UGSI Solutions, and if you're not familiar with UGSI Solutions, I'll give you a quick rundown of what we're about. We've been around for over 10 years, and we feature a number of different technologies in the water and wastewater treatment industry. One of our technologies, of course, is our PAX mixer technology. If you have a distribution system, a drinking water plant with a finished water distribution system, we furnish mixers to mix your tanks in distribution. As you know, water quality can degrade in distribution system, and by mixing your tank, you can avoid the stratification issues that can lead to water quality issues. Also, this tank mixer is kind of the first step in maintaining water quality. We move on to our PAX TRS system, which is a system to help remove THMs that may form in distribution. If you're using free chlorine for your residual disinfectant, you know that THMs can be a problem. We have a technology that will remove those THMs in distribution and maintain your water quality. We also have the monochlor RCS system. That is a system that's used with plants that are using chloramines for disinfection, where nitrification becomes an issue in distribution. And our monochlor system will eliminate nitrification issues then. So that's our water quality part of the business. We also feature the microchlor on-site hypochlorite generation system, which is seen in the photograph right here. This generates sodium hypochlorite on site using salt, water, and power, and eliminates the need to transport chemicals into your facility. The only chemical you're going to transport actually is going to be salt, which is rather safe transport then. So, but today we're going to focus on the chemical feed division. This is the division I'm involved with. We're going to talk about polyblend and dynablend polymer mixing systems, and also get into some chemical feed equipment using the Encore pumps and the Wallace & Tiernan line of equipment. Anybody familiar with Wallace & Tiernan, the old Wallace & Tiernan company? UGSI acquired the chemical feed business from Wallace & Tiernan about 9 years ago, a little over 9 years ago now. And we're based in Vineland, New Jersey with our facility then. Okay, so we're going to talk about permanganate systems first. Basically, we're going to look at potassium permanganate feed systems, dry chemical feeders, and how do you get that dry chemical into liquid form, into a solution form, with ductile systems or a tank system then. And then we'll look at how do you deliver that permanganate solution to your application point, and or how you deliver sodium permanganate solution to your application point then. So we'll talk about feeders and pump skids very, very shortly. So we'll start with the Series 32055 feeder from UGSI Solutions. Again, this is introduced for sale about 40 years ago, over 40 years ago, from Wallace & Tiernan. And again, like I mentioned, we acquired this business, so we are the the owners and manufacturers of this equipment today. There have been some refinements over the years, but the basic feeder design is still intact, and that allows you to replace any old feeder with a new feeder very simply just by sliding the new one in and taking the old one out. A lot of installations worldwide. Again, this is a volumetric feeder up to 50 cubic feet per hour. Different gearbox speeds, different screw sizes, so we really can adapt the feeder to your required feed rates. The feeder itself has a variable speed screw. We have an SCR drive variable speed screw, so we can control the speed either manually or remotely. Again, 60 to 1 operating range, so you have a wide range of operation then. And we have hopper agitation, which I'll show you right now. This kind of a cutaway of the feeder itself. We have a gearbox, motor, pulley drive, and on that gearbox is the feed screw itself, as well as hopper agitation eccentric on here. So what we do is we agitate the hopper to prevent bridging in the hopper and plugging, and also to help condense the density of the material so it's more consistent feed rate then. So this works very well with a lot of wide range of materials, including permanganate, potassium permanganate then. So hopper agitation is one of our standard features. And again, a single motor drive for a very compact system then. We do have a system designed for potassium permanganate specifically. This is for lower feed applications. We mount the feeder on a 1,000-pound stand, which is the maximum load it'll take, and we put a flushing cone on there. So we're dumping the feeder into a flushing cone, getting it wet in the solution, and from there it goes off to your application point. Low capacity is about 1.8 cubic feet per hour, and this works well if your system hydraulics will allow for an inductor like this. You can't have much back pressure on this one, so if you're going into a tank, you're above a tank and discharging into a tank, it works very well. If you're trying to pipe it into a pipeline or a system under pressure, this is probably not the right selection for you, but we have other ways to look at that then. Quick kind of flow diagram, water inlet, solenoid valve on off, 4 to 20 milliamp coming into your feeder. You can control the feed rate, the water flow rate, and then you have the feeder dumping into your eductor with solution discharge on here. What's missing, I just realized from this diagram, is a pressure switch. We do monitor water pressure, so if for some reason the water pressure was to drop off, we shut the feeder down. Here's a couple of installations. This is actually in a water plant in northern New Jersey. It was supposed to be a temporary installation, but they ended up being permanent, and they still use the bricks as part of their permanent installation then. But this is a typical feeder, vibrator for the feeder hopper. This is your flushing cone, your eductor, and of course, this is your discharge line going to your application point. Let me back up a second here. So this feeder here is a very low capacity application. So they're using 5-gallon pails of potassium permanganate to load the hopper manually. I think they'll load it like maybe once every 3 or 4 days. For larger capacity systems, we furnish a drum inverter. This gets back to what's available from Carus in the way of shipping containers for their material. I mentioned a 5-gallon pail. This is a drum of material. I think it holds about 300 pounds. So we furnish a drum inverter, pick the drum up, turn it over, and adapt it to the hopper above the feeder. And of course, then you see the feeder with the flushing cone configuration here. Kind of give you a rough idea. It may be hard to see on this little slide here, but kind of give you the rough idea of the space requirements. You do need a certain amount of height to be able to pick the feeder, pick the drum up, flip it over, and then adapt it to the feeder hopper then. If you have a system where you really can't use an eductor, we do have tank feed systems. This is basically putting the feeder on top of a solution tank with dilution water on there. We have up to 500-gallon capacity tanks. We have different sizes available. And then you're going to pump from the solution tank to your application point. So here's a little bit of a flow schematic. Same as before, water inlet, on, off, but now you're going to be feeding the tank along with your water and level controls. So now you're making a batch tank up, and you're going to pump from your tank out to your application point. This is an installation in Gloversville, New York. This is a prepackaged tank feed system. You can see here on the left, we have a 75-gallon tank. The feeder is sitting on top of that with a charging hopper above that. And next to here, which is kind of hard to see in the photo, are a couple of solution feed pumps. These are the pumps that are delivering the permanganate solution out to the application point. And as you can see here, here's the drum inverter. So we're taking the drum material, which is clamped in the drum inverter. We put a adapter cone on that with a valve, flip it over and connect it to the top of the tank and drop the entire drum into the feeder then. So that's how the drum inverter works then. We also have a system for larger capacities. The Carus cycle bin is a 3,000-pound container of permanganate, dry permanganate. We have a system where we will mount that on top of a frame, on top of a feeder tanks setup. We can add load cells in there, so we can go ahead and measure the weight of the material. We have a vibrator on there to help get the material out of the hopper then. So this is what we call a cycle bin system. Again, with larger tank capacities, typically for larger plants then. And again, here are some of the space requirements required for that. You can see here over 12 feet of headroom is required. You need to be able to position this cycle bin either with a forklift or a overhead hoist onto the top of the feeder. So you need some headroom to be able to accommodate that. So how do we get the permanganate solution from the tank system out to your application point? Well, we can use a metering pump. We manufacture the Encore 700 metering pump in Vineland, New Jersey. This pump's been around since about 1996, maybe a little over almost 20 years now, more than 20 years now, 25 years. So different diaphragm sizes depending on capacity, anywhere from 1 3/8 up to 6.5 inch. You can see as the diaphragms get bigger, the pressure capability goes down. So for high pressure application, the smaller diaphragms work well. For higher flow rates, we can go against a lower back pressure then. We do offer a duplex version of this pump, which is basically 2 heads on 1 gearbox, which doubles the capacity at the same pressure capability then. Different stroking speeds, so really the size you pump through your application, we have that kind of variety there. Double simplex option if you're curious. That's putting 2 gearboxes on a common motor drive. This way, each gearbox is independently adjustable, but you can vary the speed and from the common motor and vary both feed rates then for each pump head then. Non-loss motion design. So again, it's a variable eccentric mechanism. Gives you a very smooth output as far as discharge goes. We do have a 4-step pulley option for additional 4-to-1 operating range. So if you have a wide operating range in your plant, maybe you have a winter summer condition, we do offer a 4-step pulley to give you additional range then. We do have a clear PVC cartridge valves. So you can see here the site flow indicator, so you can tell when the pumps are operating properly. You can see the balls moving up and down. You can also tell if any kind of material gets plugged in there, and then you can know how to clean it up then. So we do offer variable speed control for the motors, and also we have an automatic stroke positioner. This is a manual positioner here, but we have an optional automatic stroke positioner then. So like most hydraulic mechanical diaphragm pumps, you require some hydraulic accessories to make it work properly. Typically a back pressure valve, pressure relief valve, pulsation dampener, and a calibration chamber then. So we do offer a pre-packaged pump skid. This has all hydraulic components already pre-piped, pre-wired to a controller if it's a VFD drive. Basically a plug-and-play situation. You bring it out to your site, hook up your suction and discharge lines, and then and your power, and you're ready to go then. We do have a standard design for a 1-pump skid, and we do have a standard design for a 2-pump skid. This would be a typical duty standby situation where you have a duty pump, and for whatever reason that pump needs to be serviced, you can switch to your standby pump and continue with your process treatment then. We do have a design for a 3-pump skid, but that gets to be kind of heavy for moving around though, but it is available then. Okay, we'll talk about we'll finish up with the permanganate feed systems. We're going to talk now about Polymer PB systems. So the agenda today is going to be to talk about the science of polymer activation. And there is a science behind that, and I'll explain what that means in the next few slides or so. Polymer activation equipment, we feature both mechanical and hydraulic activation. And again, we'll go some detail about exactly what that entails. And then some case studies. We got 2 case studies for emulsion polymer and 1 for dry polymer. And hopefully at the end, as Ashley mentioned, we'll have some time for some questions then. So polymer. Polymer does a very good job in the water and wastewater process when you're trying to separate the liquid from the solids and improve sludge dewatering. So in a typical water or wastewater plant, you're going to have numerous applications for polymer feed. Belt presses, centrifuges, screw presses, GBTs, DAFs, all these process equipment use polymer to help them work better and do what they're supposed to do, which again, separate the solid from the liquid then. Polymers are very expensive though. As you may realize, polymers are often the 3rd or 4th highest operating cost in a typical wastewater plant. Usually manpower and electrical power are 1 and 2, and polymer comes in at number 3. So it's important for your plant operation to try and minimize the polymer usage, to get as much bang for your buck out of your polymer as you can. But polymer is a tricky chemical though. It's not like your other typical chemicals that you'll buy for your plant where you just buy it in a neat or concentrated form, mix it with water and apply it to your application then. Polymer needs to be activated, okay? And how you activate the polymer goes a long way into how much polymer you're going to use in your application then. The activation requires special equipment, okay? You just can't take a simple metering pump and pump it to your application and hope it's going to work then. I've seen numerous applications, or sorry, I shouldn't say numerous, but I've seen a number of installations where they're still manually batching polymer. They're taking polymer in a bucket, in like a 5-gallon bucket, dump it into a big tank with a mixer, and hope to make it work. It will work, but you will use a lot of polymer to make it work then. So you need to look at the specialized equipment that's available for activating polymer. I mentioned the science of polymer activation. When liquid polymer and dry polymer, for that matter, first came into existence back in the late 70s, early 80s, it wasn't really understood what's the best way to activate that. Our Dr. Yang Kim, who's on our staff today, did some research back when he was with the Stranco company back in the late 80s, early 90s, to really find out what is the best technology for activating polymer. He actually wrote the book on it. It covers right here, coagulants and flocculants. And if anybody would like a copy of this book, just let us know. We'll get that to you then. Dr. Kim, he has a number of patents. He published a book, like I mentioned, a bunch of technical papers. He's also on the WEF Biosolids Committee then. So he's very much involved in biosolids, polymer activation, dewatering, all that kind of technology. So what are polymers? Polymers are long-chain hydrocarbons, okay? So they're available in different types of, different formats, different charges, different molecular weights, different charges of anionic, cationic, non-ionic, different molecular weights, and the polymer manufacturers are constantly evolving and developing new polymers, maybe different configurations, different molecular weights. So the way you pick your polymer, of course, is to do a jar test at your site and find out which polymer works best. So selecting the right kind of polymer is typically site-specific then. When polymer is delivered from the manufacturer, though, it comes in different forms. Solution polymer. This is the one exception to the rule I just talked about having specialized equipment. Solution polymer, it comes fully activated. Okay, this is typically a low molecular weight cationic polymer. It has already been activated, so you are shipping out a lot of water, but all you need to do is hook it up to a metering pump and pump it to your application point. So this does not require any kind of special equipment, just a metering pump. Emulsion polymer, which is by far and away the more common type of polymer, does require specialized equipment, and we'll go through that as what that means then. It's important with emulsion that you know what your % active content is. So if you're sizing a system for polymer feed, you need to know what percent active. Typically, 40% active is the number we go with, unless the polymer manufacturer has a different standard then. And of course, dry polymer, as the name implies, is a dry polymer, that dry powder that needs to be activated also. Dry polymer is about 97 to 98% active polymer, so it's almost pure polymer. And pound for pound, dry polymer is going to be less expensive than emulsion polymer, but dry polymer does have a little more equipment requirements to get it activated. The goal here with activation is to open up these long chain molecules and expose the charge sites. These charge sites are what does the job of grabbing these suspended solids and causing them to agglomerate or come together and form a flock and settle out then. So the whole goal here is to maintain these long chain molecules with the exposed charge sites then. So how do we do that? Okay. So when Dr. Kim was doing his research, he developed this two-stage wetting, a two-stage activation process. So what's critical here is the moment of initial wetting. This is when your polymer, either wet or emulsion or dry, first comes in contact with the dilution water. Okay, that's your moment of initial wetting, and that is critical to the operation or how you activate your polymer. As soon as the polymer starts to get wet or sees water, a sticky layer forms around there. So this sticky layer around the polymer gels, if you do not have enough high energy mixing up front, these sticky layers form agglomerations, or what we call fish eyes. So these agglomerations are wasted polymer then. So it's important to have a high shear environment as your moment of initial wetting. But if you have the high shear environment for too long a period of time, you start to destroy your long chain molecules as they open up then. So you want to transition from a high shear mixing environment to a low shear mixing environment. Okay, and again, as I mentioned, it's time sensitive then. So by doing this two-stage process, you're able to go ahead and fully activate your polymer. You can end up with three forms of polymer solutions. Again, this is your neat polymer here. I mentioned fish eyes, which is due to a poor initial wetting, or broken polymer chains by conventional mixing then. So if you mix your polymer too long, you break the chains up, not enough energy, end up with fish eyes. What you're looking for is what we have in the middle of the screen here is, again, these long chain molecules that are fully extended then. So how do I know how well my polymer is being activated? Well, one of the key indicators is viscosity. The higher the viscosity is of your polymer solution, the better job it is being activated activated then, I guess is the right word then. So activated then. So we use that as a measurement of how effective is my polymer system operating then. Even the polymer suppliers, though, they recommend a certain amount of viscosity as a target when you activate the polymer then. So they recognize the fact that viscosity is important to evaluate how effective your polymer activation is. One thing that's often overlooked is the quality of the dilution water. Very important to make sure you're, again, activating your polymer properly then. Hardness is a problem, can be a problem, and anything over 400 parts per million, you may need a softener to reduce the hardness. Soft water helps the molecules extend faster. The real one that we see most of the issues with is with chlorine content. If you're in a wastewater plant and you're using reclaimed water for your polymer activation, it's typical to have a fairly high chlorine content. Anything over 3 parts per million can cause your end up using more polymer then. Temperature is also an issue. Mostly on the low end of the spectrum here. Anything lower than 40 degrees Fahrenheit really slows down the activation of your polymer, and you may need to temper your water up to about a 50 to 60 degree range. Depends on what polymer you're using, but most of them are really affected by low water temperatures then. Over 100 degrees Fahrenheit, it could also damage the polymer chains. You're not going to typically see that unless you're in an industrial application then. Suspended solids, you want to keep those out of the dilution water. And pH, negligible effect. So if your pH is anywhere between 3 and 10, it's not going to have much of an effect on your performance. I mentioned the effect of water chlorine content. You can see as my chlorine residual goes up, my viscosity starts to come down and really takes a downward turn around the 3 part per million range. So be aware of how much chlorine content you have in your dilution water. Okay, so one-stage versus two-stage mixing. When polymer systems first came out, like in the mid 80s, it was a single-stage mixer, and this is an example of one here on the left-hand side. The number, by the way, the number in red is what we call the G value, which is the mean shear rate. It's a measurement of the mixing energy inside this mix chamber. Then, so you can see with a single-stage mixer, you have a pretty much uniform mixing energy throughout the entire mix chamber. Then, with a two-stage mixer, we put a baffle in there to separate the low energy zone from the high energy zone, modify the mixing impeller a little bit here. You can see here that we have a 4,000 G value in the high energy zone versus the low energy zone. So what it all mean is that when you compare polymer made up with a single stage mixer, which is the green bars, versus a two-stage mixer, you can see a pretty significant increase in the viscosity of your polymer solution. That's significant. That 22% or 37% increase has this profound effect on how effective your polymer is going to be and how much polymer you're going to use in your application. So that's why we say two-stage mixing is pretty much the norm today, but this is what was developed over the years by Dr. Kim and his research. Then. Okay, I have a illustration here. Okay, so this is a mixer on a polyblend M system. This is a mechanical mixer. This is a high-speed impeller here. You can see the agitation going on the right-hand side here. The water flows through the baffle plate, and you can see over here a much lower energy zone. This is your high energy zone, low energy zone there. So this is key to your two-stage mixing device. We call it that. This is a two-stage mixer then. We injected some air here to give you an idea of what it looks like, but in real life, you can actually see the polymer mixing through the mixer through the baffle plate into the low shear zone. The polymer suppliers, they recognize this. They do recommend two-stage mixing. Okay, so this is something that, again, that they recognize, which helps get their polymer to work better, and that's their goal. They want their polymer to work, otherwise nobody's going to buy it then. So they recommend discrete two-stage mixing then. Talk about two-stage mixing. This is a test that was done, and I'll go into more detail on this one a little bit later on in the presentation. But this is a pilot that was done by Jacobs Engineering in Gwinnett County, Georgia, just outside of Atlanta, about 2 or 3 years ago, confirming that two-stage mixing has a significant cost savings over single-stage mixing. At this particular plant, the savings are over $200,000 a year going to two-stage polymer mixing versus single-stage mixing then. So again, that can be quite significant depending on how big your plant is then. In this case here, the projected savings would pay for the polymer equipment in less than 2 years then. Another thing is we talked about the secondary zone or low energy zone. You need to have enough residence time inside that low energy zone for the polymer to fully open up. Again, this is a time phase situation then. So we modified our mix chamber about 4 or 5 years ago. We increased the low shear zone, or low energy zone, by a factor of 3, and now go to a much larger mix chamber than which you saw in the video. So even here, doing some testing in our shop in Vineland, we had a little bit of an increase in the viscosity going to the larger low energy zone mix chamber then. Even this little bit of increase though has a significant effect upon the amount of polymer used, and I'll show you that in one of our case histories then. And again, going back to what the polymer manufacturers recommend, they recommend enough residence time in that low energy zone. This is kind of high, 10 to 20 minutes, but we found out from our experiment that by increasing the volume 3 times, we had a significant increase in viscosity then. One more thing, and it gets kind of confusing here, is we talk about two-stage mixing is two-stage dilution. The reason for this is that the polymer manufacturers, they inject what they call an inverting surfactant or breaker surfactant into their emulsion polymer. This is to help the polymer activate or invert, or because it is an emulsion, you want to get it out of the oil bath into a water solution. So this inverting surfactant works very well when you have a 1 to 1.25% concentration in your mix chamber. Problem with that is, though, that most applications require the final solution to be anywhere from 0.25 to 0.5% concentration. If you mix it up at this concentration to begin with, you're not going to realize the benefit of the inverting surfactant, and again, end up using some more polymer then. So ideally, you want to mix it up at a higher concentration and then post-dilute that or second dilute that down to your final concentration. And that is what we do with the polyblend system. We have secondary dilution on there as standard then. By the way, there's also an AWWA standard for polymer that talks about realizing the benefit of the inverting surfactant and making it up at a higher concentration before you finally get down to your diluted concentration. So, in kind of sum this up here, we want energy at the high energy at the moment of initial wetting. We need to have some transition to a low energy zone, adequate residence time, and if you do all that, you'll end up with a fully activated polymer solution. So let's talk about equipment real quick here. So I mentioned that UGSI, we feature both the mechanical polymer activation with the polyblend equipment or hydraulic or non-mechanical or hydraulic mixing with the Dynablend equipment. Just in case you're not aware, we did acquire the Dynablend line of polymer feed equipment, I think about 3.5 to 4 years ago. So it's now part of our standard product offering. Again, all manufactured in Vineland, New Jersey. So mechanical mixing, we can measure the mixing energy. There's a motor on there. We can actually calculate and measure the G value, which is the mean shear rate. And you can see here with the mechanical mixer, again, time dependent, you have your high energy zone initially, and then as time goes on, and as the solution flows through the mix chamber, this tapers off into a much lower energy mixing environment then. With hydraulic mixing, since there's no motor involved in that, you really can't calculate a G value, but you can look at what we call the magnitude of force versus angle. This is the force that's implied when you inject your chemical into your water stream. The lower the angle is, the less energy you're going to have. So, for instance, we do a 90-degree injection angle. That gives us the most energy up front. Some other systems out there go more of a tangential type injection angle, like a 45-degree angle. And you're not getting the maximum amount of energy up front then. I keep stressing the fact that we need to have as much energy as possible at the moment of initial wetting. So I mentioned real quick that the polyblend, Dynablend systems, again, we all been around for many years, 1,000 installations worldwide. We do follow the science, obviously. Mixed energy profile, 2 stages, the chamber volume, and the residence time. So it comes down to the fact that which way do I go? How do I know if I want to go with a hydraulic mixing device or a mechanical mixing device? We can help out with that selection. We look at different criteria depending upon the application, operator experience, plant services, for instance. Since the hydraulics, the Dynablend hydraulic system is more water pressure dependent. If you have a varying water pressure in your plant or a low water pressure in your plant, maybe mechanical mixing may be a better choice then. Or if you put a booster pump in. Specialty applications, you have explosion proof, right? In a hazardous location, it's easier to make a Dynablend system suitable for explosion proof than polyblend because there's no motor involved, there's no mixture motor involved. Space constraints, for instance. The Dynablend system is tall and narrow. The polyblend system is more wider and shorter, put it that way then. So we look at different criteria to see what's the best solution for you. Bottom line is, if we're not sure, we look at polymer type. We are doing active testing at our facility in Vineland to test different types of polymer with both the hydraulic and mechanical mixing to see which technology works best with that particular polymer then. So if we're not sure which way to go, let us know what kind of polymer you're looking at, and we'll see if that's one of the ones we've tested, or we can test it, and let you know is mechanical or hydraulics the best way to go for your best activation. All right, I mentioned the Dynajet system. This is a two-stage hydraulic mix chamber. This is your water inlet here. You got a 70 foot per second water stream coming into a polymer injection point. Then you go into a more concentric baffle, which is your quiescent zone. I mentioned the force angle, the magnitude of force versus angle. This is the injection angle here. Again, it's at a right angle, 90-degree angle. So you're getting the maximum amount of energy up front at the moment of initial wetting, and then it goes into your baffle concentric rings or your low energy zone. This can be either a manual adjustment on your water flow or a automatic adjustment with what we call a lavo, which is a automatic motor operated orifice adjustment. Typical system here. This is the Dynajet system. This is a smaller mix chamber. This is a 4-inch mix chamber. We go as high as a 12-inch mix chamber for high capacity. But you can see here that vertical orientation, the polymer pump can be either a peristaltic, a diaphragm pump, progressive cavity pump, whatever preference you have, or depending upon what capacity you're looking at, we can obviously select the correct pump for that too then. I do like progressive cavity pumps. They don't tend to plug up with any kind of polymer gel that might get in there. They work very well. So, and you can see everything is self-contained here. With Polyblend, we have a motorized mixer. You saw the video. This is a motor, direct drive motor, and a high-speed impeller. This is your dividing baffle here from high shear to low shear zone. Your polymer solution comes out of here, and here's where you inject your secondary dilution water. This is to get your dilution down to your final concentration then. Okay. So again, choice of, you saw the slide already. This is your tapered mixer profile then. This is your typical setup. You have the frame, stainless steel frame. This is a progressive cavity pump on here, mixing chamber, control box. Everything is all self-contained. You bring the water inlet in, polymer inlet from your tote or your drum or whatever your polymer source may be, and then you have your polymer solution output then. So again, this is what we call a flow-through system, as is the Dynablend unit. So you go right from this system right to your application point. There's no need for an aging tank. Aging tanks were something that was required many years ago because, again, it wasn't fully understood how to activate the polymer. But this case here, we do not require an aging tank, and right to your application point then. For low capacity systems, we offer the Polymer PB Series. Again, this is a very compact system, anywhere from 15 to 1,200 gallon per hour of polymer solution. It has a little pump in here. It's kind of hard to see in the photograph. That pumps the polymer. This has been around for many years. Very popular. Very compact. You can fit on a shelf. You can sit on top of a drum. You have a lot of different applications or different mounting applications for that. The mini blend for fluid dynamics, again, it's kind of the same capacity range. It is, again, very inexpensive and used for pretty simple applications then. For larger size systems, again, we talked about the Polyblend M series up to 12,000 gallon per hour, and the Fluid Dynamics Dynablend up to 21,000 gallons per hour. 21,000 gallons per hour, we use a 12-inch mix chamber on here, which is obviously much larger than the 4-inch one we show here. So again, depending on what capacity you have, we'll size the system for that. Typical operating range of this system is about 10 to 1. So if you're feeding 2,400 gallons per hour of solution water, you get down to about 240 gallons per hour for your operating range then. So that's basically your operating range you want to consider. For controls, you have two variables on here. You have either water flow or polymer flow. So you have two variables you want to control. A control, or level 3 control as we call it, strictly 4 to 20 milliamp input to control your polymer feed pump. Your dilution water is manually controlled. So the operator is going to control the dilution water flow rate, going to set the flow rate, leave it alone, and then if you need to change your polymer solution, you change your need polymer feed pump then with a 4 to 20 milliamp. Remote start stop, so you know turn it on, turn it off when you turn your press on or off then. Going up a level of controls is the B or B plus or level 4 or 5 controls. Same function as the A controls. You're still manually controlling the water flow, but now you can set into your controller a percent concentration that you want of your solution. Let's say you want a 0.4% solution concentration. What will happen then, the B control will control the neat polymer pump to maintain that 0.4% concentration. So as your water flow changes up and down, if you have a water fluctuation or you want to increase your solution feed rate, the controller will automatically pace the neat polymer pump to maintain the same concentration. What we need by B plus or level 5 is those are PLC HMI type systems, which have a lot more control functions in there and can integrate with your SCADA system, your Ethernet system. So again, they talk about this is manual water control. The top level control, C control level 6, this is where we automatically modulate now your water flow too. So from a remote location, you can control the water flow as well as the neat polymer flow. Again, you can set a concentration set point, and let's say I want to vary my solution flow from 1,000 GPH to 2,000 GPH. That's all done remotely and maintaining the same concentration as you need then. So again, this is a totally automatic system for remote control. All systems here, we always monitor the water flow. If there's a water flow issue or the water pressure drops off or the water flow drops off, system goes into alarm and we stop feeding polymer. You do not want to be feeding polymer into a mixed chamber that is not seeing dilution water there. Okay, moving on to dry activation systems. Pretty much the same concept as liquid polymer, with one notable exception that dry polymer does require aging. Okay, you need to have an aging tank in your system to age for dry polymer. Then you just cannot get it wet and then shoot it out to your application. It needs to have aging time. So with the polyblend, we have a mechanical mixer. Again, we have a high-speed impeller. We have a dry polymer coming in from a feeder. Water in, water out, and then this is your high shear moment of initial wetting. This is your high shear environment then. From here, it goes out to your age tank, which is your low shear mixing environment then. So, oops, let me back up here. So yeah, so this is your high energy mixing up front, and it goes to an aging tank, which is low energy mixing. So we're still doing two-stage mixing, high energy, low energy, but now it's more of a discrete process where you have a low energy mixing tank to age your polymer then. For Dynajet, which is pneumatic hydraulic mixing, pneumatically conveying the polymer into the mixing head. This is a high energy jet spray wetter. This is your moment of high energy, moment of initial wetting for this system. You're going to be conveying the polymer pneumatically, so this gives a little more flexibility as far as layout goes in your system then. But again, it just gives you the same type of technology that we have with the mechanical system. So especially for dry polymer systems, why is this high energy mixing so critical? Well, some guy named Tanaka many years ago theorized that the polymer dissolution or aging time excuse me, is a function of the diameter of the particle. So if we have a particle that is, let's just call it 1D in diameter, it takes 1 minute to activate that. If you have a particle that's 10 times that size, 10D, it's going to take 100 minutes to activate that then. So that's why it's so critical when, especially with dry polymer, when you first get this stuff wet, that you want to avoid these larger particle sizes. You want to have the smaller particle sizes then. So that's why we have the high energy mixing up front. Again, no fish eyes, and then shorter mixing time. And yeah, exactly. Shorter, so you have shorter aging time, the better you activate or better you wet your polymer. The second stage I mentioned is mixing. You have to mix this tank in the second stage as your low shear zone. This does create a little bit of a problem though, because if you put a conventional bolt prop mixer inside your aging tank, you're going to have a high shear environment right around the mixer tips here, which is in this case here it's a 300 G factor. So, so you're going to be damaging these chains as they open up in this mixing environment then. And the longer you run the mixer, the more damage you do to your mixer chains then. So to get around that, we looked at a different impeller design, what we call a hollow wing impeller. So we increased the diameter of the impeller and slowed the impeller down. So now you have much less shear at the impeller tips here, and still able to get full mixing of your tank. So this is what we look at as far as uniform mixing of your tank then. One thing though we do have to be concerned about is what's called the Weisenberger effect. Not widely known, but it is something we need to be concerned about with polymer mixing. You can see here with a beaker with a typical mixture on there, with water, which is Newtonian fluid. You put a mixture in there, you get a vortex. Everybody sees that. That's pretty common with any kind of Newtonian fluid. With a polymer solution, which is non-Newtonian, the same mixture, the polymer ends up climbing up the mixture shaft. Okay, because that's the way that this pseudoplastic solution works. And what happens there, of course, is you get very high mixing energy at the impeller tips and very low above and below that then. So you don't have very uniform mixing, and you're wasting polymer climbing up the mixture shaft. This is the example of one that we did. Oops, there we go. So you can see here, this is a 0.25% concentration and a 0.5% concentration of polymer. So what this tells us is that when you're making up a dry polymer solution, you want to keep your concentration lower to minimize the effect of this Weisenberger effect. Lower concentration means bigger tanks. You need a bigger mix tank now, because now instead of making up a 0.7 or 1% concentration, I'm doing a 0.25. I need to have a much larger tank to meet my capacity then. So we took a look at that and realized, well, we need a better way. So we invented this hollow wing impeller, which is what we see right here. Okay, and by having a plastic sleeve over the mixture shaft, we eliminate the Weisenberger effect. So this allows us to make up a much higher concentration of solution. So instead of a 0.25 or even a 0.5, we can go much higher than that then. Again, a low RPM mixture, we go to a square tank design. This doesn't require baffles, and also it's more efficient from the use of space then. So, and all this leads to much shorter mixing time then. So where the manufacturer may recommend, 60 minutes of aging time, we can do that for much less time than that. Actually, as a matter of fact, over aging can damage your polymer. So we look at that as being a detriment then. Then here's another photograph of the mixture itself. There's a PVC sleeve around the mixture shaft. This is your hollow wing mixture here. And of course, the solution comes out the tips of the mixture there with a low shear zone. And you can see here, this is a 0.75% concentration. And we've created a vortex, like you see with a Newtonian fluid, around the mixture shaft. None of that Weisenberger effect. And here's this is our test tank in our shop in Vineland. Again, this is a 0.65% concentration. And you can see here again, no Weisenberger effect. So by using this mixture technology, we're able to put in smaller tanks, higher concentration then. Typical layout. This is your typical layout for a system. You either have a two-tank system, you have a mixed age tank, a transfer pump, and a feed tank, or you can have a flip-flop tank situation. Or for lower capacity systems, we have a stack tank configuration. The top tank is your mix and age tank. When it ages out, when it fully ages, you transfer by gravity to the bottom tank, and the bottom tank becomes your feed tank then. So to feed the solution out to the application point, we have what we call post-dilution skids. So I'm making the batches up anywhere from 0.5 to 1%, but I only need 0.1 or 0.3% at my application point then. So we have a progressive cavity pump on here. It'll pump to higher concentration, and then after the metering pump, then we'll post-dilute it down to your final concentration. This way you use it's a much smaller, less expensive pump, and then you just use the post-dilution after the pump to get to your final concentration. So that is the way to handle the dry system. And with a dry system, because you're doing a batch with an age tank or a feed tank, you can hook up multiple pumps to multiple points of application. So I've seen systems where you have a single dry feed system and you're feeding 3 or 4 different presses or different centrifuges with the same polymer from the same make-down system. Okay, getting on here, talk about a couple of case histories. This is the Chamonix water treatment plant outside of Philadelphia, PA. This is a system here, kind of a medium-sized system, 15 MGD. This is a system that we wanted to prove out our technology on the extended mix chamber. This is an ideal plant for that. They had 2 identical combine Sanderson belt presses running the same sludge. Each one was fed by a polyblend system. This is an older style system here. They had 2 of these, one for each belt press. We came in with our polyblend with the extended mix chamber. The photograph a little bit skewed here. Both these skids are the same width in real life, but the photograph kind of skewed this one here. It makes it look a lot wider than it really is. So here we have the extended mix chamber. This is the older style mix chamber. We ran, again, run the polymer to the two presses side by side using the same sludge. So you can see here the results were, with the blue line is with the older system. And you can see the polymer usage per ton of dry solids here. The red line was with the extended mix chamber. So just by extending that mix chamber, actually tripling the size of that secondary low energy part of the mix chamber, we were able to reduce our sludge volume by about, polymer volume by about 30%. And we improved the sludge cake slightly, a little better than that. So we did a better job of activating the polymer with the extended mix chamber, as you see here in a little diagram in the bottom corner here. That extra space gave us a better performance then. Another case study here. This is a Fairfield Suisun district outside of San Francisco. This is a dry polymer system. They're using polymer for dewatering with the screw press and thickening with the GBT. And they've had an older polymer system, dry polymer system for many years. They were struggling with trying to make a consistent polymer solution, a lot of maintenance issues. This is their older system here. Again, they had a couple of 4,600 gallon mix tanks for this one with anywhere from 2 to 6 hour aging time to try and get their polymer fully activated. And that just tells me that with that long of aging time, they were not doing a good job up front of getting this polymer wetted, and you have these larger diameter polymer molecules in. We brought in one of our demo trailers, a dry prep demo trailer. This had 2 360 gallon tanks on there with the hollow blade impeller we just talked about, energy mixing zone here. This is actually in operation. This is the feeder dry polymer flowing into the vortex created by our mixer. Results were about a 40% savings on the screw press application. So you can see here over 2012, 2015, that was their usage per dry ton. They bought in the demo unit and immediately cut their polymer usage by 40% on the screw press. And at the same time, we're able to increase the throughput through the screw press then. So not only did it lose less polymer, you had a better activated polymer to work with the screw press then. Result of that, of course, was that well, these savings alone paid for our new system in less than 2 years then. And it had the same kind of savings on the dewatering, or sorry, the thickening press too then. Okay, last case study. This is the, I talked about this previously. This is Gwinnett County, Georgia, the F. Hill Water Reclaim Center. Pretty good sized plant, 60 MGD. Their annual cost for polymers, $1.2 million. 400,000 on thickening, 800,000 on a centrifuge. For years, they were using a single stage polymer mixing system. Jacobs Engineering was hired to come in and do a pilot test to evaluate what's the best way to reduce our polymer consumption. So Jacobs set up 3 polymer systems for the pilot trials. The existing equipment was a Flowquip system. This is what they had on site. We provided one of our polyblend systems, MM 2400, which is 2400 gallons per hour of polymer solution and 30 gallons per hour of neat polymer capacity then. And Prominent brought in the ProMix system, a little bit larger system, but kind of the same capacity. Again, 1-stage mixing, 2-stage mixing with us, and then Prominent claims 3-stage mixing. So results of the test were, and I'll show you some better numbers in a minute here. You can see that the test was done with two different runs. Each pilot was done as using the Flowquip unit as the benchmark, and then they ran that against the Polyblend unit in one trial, and then ran against the Prominent unit in the second trial. So always comparing the numbers to the existing Flowquip system. And you can see here the red line being Polyblend. You can see that as the trial ran on, they were able to dial down and really reduce their polymer use dosage per ton of dry solids. Same thing with the Prominent unit. As the pilot ran, they were able to dial down and reduce their usage too with the Prominent unit. Not only that, we got a better centrate. This photograph here is the existing centrate with the Flowquip system, single stage mixing, and this is the centrate with the polymer system. So a much clearer centrate. This knows that their polymer is doing a better job of grabbing those solids and taking them out. Results were with the pilot one, we had about a 24%, a little over 24% savings in polymer compared to the existing system. With the Prominent system, about a 10.5% polymer savings. So again, multi-stage mixing just proves that multi-stage mixing is much more effective than single-stage mixing. So you're going to ask the question, well, if we had 25% less polymer with the Polyblend system and 10% with the ProMix system for Prominent, both are multi-stage mixing environment. What's the difference? Well, I'll take you back a couple of slides here. The difference is that we have a mixture running at 3450 RPM at the moment of initial wetting at the high shear zone, whereas the competition uses a 1725 RPM mixture. So half the mixture speed, I don't know if that translates to half the mixing energy, but less mixing energy up front. And the result you can see here is that much better performance with the higher mixing energy up front. Again, that gets back to that moment of initial wetting that we keep talking about as being so critical. Okay, trying to wrap this up real quick. We do have a demo program available. So if you're not sure if your polymer system is going to work better or whatever, we do have a number of liquid demo units available. We also have 2 demo trailers available with the dry prep system. So if you're looking for a demo, contact Carus, and we'll work with them to put together a demo package then. We do have a sizing guide on our website. So if you're not sure what size system you need, we do have a sizing guide for neat polymer mixing then. This is just some of the numbers that we use. The drier you're trying to get, sludge dewatering uses more polymer than thickening, than clarification and filter aid. So that's just some of the guidelines that we have. Okay, quick summary for polymer mixing: good quality dilution water. If you're looking for that first. Following the science: 2-stage mixing, sufficient residence time, and 2-stage dilution for emulsion polymer. The dry polymer, again, 2-stage mixing. Your aging tank needs to have low speed uniform mixing to prevent that Weisenberger effect. Okay, I think that about does it. Maybe I have time for a few questions. So Ashley, let me know if anybody has any questions.
Hi, Gary. That was good information, and it looks like we do have a couple that came in. If anyone has any additional questions, feel free to enter those into the question pane in the GoToWebinar panel. The first question, Gary, why would the application of mixing energy to polymer be considered tricky?
It's tricky because you want to be careful with the two-stage mixing. You don't want to have too long of, I guess, mix time at the high shear level, because as the polymer chain starts to open up, they become more fragile, and that's why you want to transition from the high shear zone to a low shear zone. If you have too much time in the high shear zone, then you're defeating the purpose. You're opening the molecules up and then chopping them up, and they become less efficient then.
Okay, awesome. And then we do have a few requests for the PDF of the presentation, so I'll be sure to send those out also. Okay. Next question, can both hydraulic and mechanical mixing adequately activate polymer?
The question is yes, it can. Yeah, both feature the same type of technology, high two-state mixing. Now we found that some polymers behave better with hydraulic mixing, some behave better with mechanical mixing, which is why we're under this doing this program right now of testing these polymers in our factory in Vineland, New Jersey, to find out which one gives us the best results. But bottom line is that both technologies do a very good job of activating polymer.
Okay, perfect. Thanks, Gary. I think that's all of the questions. Like I said, there were a few requests for the presentation, so we'll be sure to send that out. Thank you, Gary, for your time today and the presentation, and thank you everyone else for joining.
Hey, thank you everybody for your time. Appreciate it.